Welcome to Solutions to Homework Set number 8 for ECE 320. The first problem is implement the following logic using NAND gates. With NAND gates, the trick is to circle the ones. I want to circle all the ones. The X's are don't cares. If I circle them, that's okay. If I don't circle them, that's okay. The trick is to find powers of 2. I either want to circle 1, 2, 4, or 8. Have the biggest power 2 that you can, and that makes the simplest logic. So one way is to get these ones. I'll circle the top one in green. To get this one right here, I've got that group of 2. Then for this one, a group of 4. For these two, or that one, group of 4. So that would be A bar B bar, or A bar C D bar, or the red line, A C bar, orange line, A D. So there's the logic. To implement that with ANDs and OR gates, that would be A bar and B bar, or, so ignore the red circles for now, or A bar, C, D bar, added together, ORed with A, C bar, and so on. Once you get the logic, the trick to do NAND gates is throw in a double negative. A double negative doesn't change the logic, but AND NOT is a NAND gate. And not AND, or not OR, is also a NAND gate. So this is how you implement it with NAND gates. Basically, you circle the ones to implement logic with NAND gates. Problem 2 is repeat, but now using NOR gates. With NOR gates, you circle the zeros. So in this case, I'll circle these 2 zeros. I'll circle these 2 zeros and these 2. And that's about the best I can do. So that would be Y bar, since I circled the zeros, is this guy. That's A bar, B, C bar. The red is A bar, B, D, and the green is A, C, D bar. Now use De Morgan's law. Throw in a double negative. I negate the left-hand side, negate the right-hand side. Not Y is just Y. With De Morgan's law, AND becomes OR becomes AND you change the logic. A bar becomes A, B becomes B bar. So there's my logic. To implement it, I would take A or B bar or C, ORed it, again ignore the red circles for now. That gets ORed together, ANDed with A, B bar, D bar, so here's A, B bar, D bar, ANDed with A bar, C bar, D, A bar, C bar, D. And the trick again is to convert to NOR gates. I throw in a double negative, OR NOT is NOR, NOT AND is also NOR. So to implement logic using NOR gates, I circle the zeros. Problem 2. Okay, the other problem 2, I miscounted. Problem 3 is find the voltages and currents for this DTL OR gate. So one of these is a NOR gate, this is an inverter, a NOT NOR is OR. So this is the reason we like NOR gates. You only need one transistor. It takes 2 transistors to build an OR gate. So anyway, back at the ranch. To figure out which diodes are on or off, I've got 5 volts going to ground. That's trying to push current through here. The current then is 5. I've got 1, 2, 3 diodes. 5 minus 2.1 is 2.9 volts. 2.9 volts at 40K is 72 microamps. That allows beta IB, allows 7 milliamps to flow through the collector. I'm only trying to push 2.4 milliamps, so this one saturates, and this becomes 0.2 volts. When V3 is 0.2, I need 2.1 volts to turn on these 3 diodes. That's not enough, so these turn off. When this is off, I have just a voltage divider. 40 over 40 plus 2, 4.76 volts, with that percentage of 5 volts. And I guess that's everyone. So this is an OR gate. If either one is 5 volts, I get current flow. If there's current flow, the output becomes high. If I simulate this in Circuit Lab, here's what I get. And the voltages aren't exactly the same. The reason they're not exactly the same is I said that V1, this is 0.7 volts. For an ideal diode, the drop is 0.7. Actual diodes, it's close to 0.7, but not quite. Let's see, where's V2? V2, this should be 1.4 volts, 0.7 plus 0.7. Circuit Lab says actually it's 1.2 volts. Again, the voltage drop across the diode isn't exactly 0.7. At V3, I assume this is saturated, 0.2 volts. 0.2 is just kind of a random number, close to 0 but not quite. Circuit Lab says it's actually 0.06. And V5 is actually almost dead on. When this transistor is off, it's just a voltage divider. Our calculations are pretty good for voltage dividers. Problem 4, this is a DTL AND gate. If either one is 0, the voltage goes low. So this is kind of a min function. This one turns off, the 0 is less than 0.1, so all the current goes this way. Makes this 0.7. I've got two diodes to the right. I need 1.4 volts to turn these on. 0.7 is not enough, so these turn off. If that turns off, this becomes 5 volts. When this is 5 volts, I'm trying to push current backwards through this diode. It turns off. So this is isolated. That just becomes 5 volts and 0 milliamps. Over here, I now have 5 volts going to ground through this path. This becomes 0.7 plus 0.7, 1.4 volts. The current then is 5 minus 1.4 over 40K, 90 microamps. All of it goes over here. This allows 9 milliamps to flow. I'm only trying to push 4.8. This is wrong. 2.4 milliamps through it. So 90 is more than 2.4. This saturates. Problem 5 is if I try and run this in Circuit Lab to see what the voltages are. Again, it's pretty close. I think that V1 should be 0.7. It's actually 0.526. Again, the voltage drop across the diode isn't exactly 0.7. Everybody's off, so V2 is correct, it's 5 volts. V3 should be 1.4 volts. It's actually 1.2 volts. These voltage drops aren't exactly 0.7. And V4 is saturated, should be 0.2, actually 0.06. Problem 6, Ttl Logic. This is kind of confusing. This transistor is the same. This is an NPN transistor. If I use it the correct way, then the gain is 100. If I use it incorrectly, it's still an NPN transistor, but due to the doping, the gain's lousy. So this direction, incorrect use, the gain is 0.4. Here the gain is high, 100. Take the left-hand side. When this is 0 volts, this is the path to ground. This becomes 0.7. I need 0.7 plus 0.7, 1.4 volts to turn this on. That's not enough, so the transistor turns off. And I have 5 volts out. So this is a TTL inverter. 0 volts in gives you 5 volts out. A little bit less due to voltage division and loading. At the other hand, if this is 5 volts, now the current flows right. I get 0.7 plus another 0.7 makes 1.4 volts. The current is 5 minus 1.4 over 20K, 180 microamps. That flows through here. The collector current is beta IB. This will actually be 0.4 times IB, 72 microamps. The two add together gives you 252 microamps. This allows 25 milliamps to flow. I'm only trying to push 5 milliamps, or 4.8 milliamps, so this saturates. And the voltage is 0.2. So that right there would be 4.8 milliamps. If I check in Circuit Lab, it's pretty similar. When the input is 0 volts, V1 is 0.7-ish. V3, this is turned off. By voltage division, that one's correct. And the current over here is 215 microamps. That's this current flowing that way. That's the loading you're going to see. At the other extreme, if I make this 5 volts, now the current flows right. I expect V1 to be 1.4 volts. It's actually 1.382. V3 over here, I expect that to be 0.2 volts. It's actually 0.03. And when you saturate, it's not exactly 0.2. That's a ballpark guess. If I want to find the beta of this transistor when it's used backwards, I can find this current. This is 72, actually 720 microamps. I expected 72. The current through the base, through V1, is 904 microamps. From that, I can calculate the gain of the transistor when used backwards. It is 4. So I assumed this way, used backwards when current goes this way, beta is 0.4. The one in Circuit Lab, when used incorrectly, the gain is 4. Now, part of the reason that this current is a little bit different. And kind of a sidelight, I'm using a 3904 transistor. 3904s are not designed for Ttl logic. If I built a gate, I could change the doping so that the gain would be 0.4 rather than 4. Less gain is good because less gain means less current being drawn from the source. Problem 8. Give or take some numbering problems. Okay, problem 8. Problem 8 is I want to build this circuit. This is similar to what we did a couple weeks ago using a transistor switch. I can build a temperature alarm. This guy right here is a 555 timer. When the output goes low, current goes left. When the output is high, current goes right. So I can turn on and off this 3904 transistor from the 555 timer. This is my on-off. If this is 0 volts, current always goes left. This is always 0.7. This guy's always turned off. When this is 5 volts, this guy turns off, and I have my 555 timer driving it. So I can turn on and off the speaker with this signal. So illustrating that, here's my circuit. Find a pencil or something to point with. These are my 3 diodes coming together. Here's the diode that goes to my comparator. If I turn it on, if I take that guy and tie it to ground, the speaker turns off. Tie it to 5 volts, speaker turns on, speaker off, speaker on. I'm not going to take that to a comparator. The comparator compares the voltage across a thermistor to the voltage from a potentiometer. And here's the voltage on the potentiometer. I got a lot of glare in this room. There, 7.31 volts. If I look at the voltage drop on the thermistor, this should turn on and off at 2.31 volts. That's better. So take a hairdryer and warm it up. As it warms up, the temperature will increase, the resistance drops, the voltage drops. And there you can hear it. At 2.31 volts it turned on. As I let it cool off, it should turn off at 2.31 volts. .29 volts. Again, going again. And that's not too bad. Warming it up. It's kind of hard to hear over the hairdryer. .38 volts, it turned off. So that was just building in hardware. Should match what you calculated. This voltage right here is how I control where it turns on and off. That's basically my thermostat. Whatever voltage corresponds to the temperature that I care about, switch at that voltage. When it gets hotter, this voltage drops, and the alarm goes on. When it gets colder, R goes up, voltage goes up, it turns off. And if you do the calculations, I can sit there and calculate what it should be at 0 volts. 0 volts is off. When this is 5 volts, it turns on, enables this part. In Circuit Lab, I can check when this is 0 volts, V4 is 5 volts, this is turned off basically. When they're both 5 volts, then this turns on, and that becomes 0.2. So if either one is 0, it's turned off. So when this is 0, that disables it. When this is 5 volts, then this one can go on and off with a 555 timer and make the speaker play. And here's what the circuit looks like. Here's my 555 timer. Here's the output of the 555 timer. Goes to a diode. This is going this way. You can tell by that line. That line corresponds to this guy. Here's the other side of the diode. That's this part of the circuit. The one goes to the transistor. That's over here. And let's see, where does it go? This guy right here goes to your output. If this is grounded, that brings this 0.7 volts and turns off the transistor. When it is 5 volts, this guy basically just has no effect, and I'm driving the 555 timer, then drives this guy. So there's the circuit and the circuit board. This is a 602 op-amp for a comparator. Again, homework set number 8 for ECE 320.